We're now going to talk about the graphs of derivatives. So this is something you may have seen before in maybe like an introductory physics class when you were taking the graph of the position of a car and comparing it to a graph of the velocity of the car. Velocity is considered the derivative of the position. So the rate of change of the position of a car would be the velocity of the car, and then the rate of change of the velocity of the car would be the acceleration of the car. And so there are problems in like an introductory physics class where you have to know the connection between the graphs of the position, velocity, and acceleration of the car. And so if you've done this before, you know this can be quite challenging. You really have to concentrate and think. Conceptually, it's not too bad as far as the derivative here is just the rate of change of a function. So if I'm given the graph of a function, so we're going to start with this one, okay? And this is a nice one because it's always a constant rate of change over different intervals, okay? So the derivative here, the graph of the derivative, the value of the derivative is just the rate of change of the function at each point, okay? So the value of the function is, the point on the graph, but the rate of change is the slope of the tangent line of the graph, okay? And so what we see here is this has a constant rate of change over each of these intervals. So what I'm going to do for this graph is I'm going to start out by just finding what the rate of change is over each of these intervals. So over this one, the change in y is 2, and the change in x is 4, and so 2 over 4. So the slope here is 1/2. So I could say like the f prime of x on this interval is 1/2, a positive 1/2. Okay, well what about this interval? So the change in the y values is 4, and the change in the x values is just 1. So f prime of x on this interval would be 4 over 1, negative 4 over 1, so this would actually be negative 4, okay, just on this interval. So from here to here, the graph isn't changing at all, right? It's a constant. So on this interval, the derivative is just 0, right? And then from here to here, okay, the y values change 4 and the x values change 2. So on this portion of the graph, f prime of x is a positive 4 over 2, so a positive 2. Okay, and so the derivative then on each of these intervals is a constant, and its value is given right there. So it's a pretty easy thing to do the graph here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So there's like negative 4, 1, 4, and 6. So these are the main x values. So from negative 4 to 0, it's going to have a slope of 1/2. So maybe I'll do 1, 2, 3, 4. 1, 2, 3, 4. So negative 4 to 4. And so from negative 4 to 0, the slope of the graph is a positive 1/2. So it'd be like right here. And at the end point, when you have an end point with nothing on the other side, then the derivative does not exist at that end point here. And so then it goes like this. Though we can define the one-sided derivative, and if we define the one-sided derivative, then technically it would exist. So I'll actually put a closed dot there. Okay, but then when we get to 0, the derivative is not defined. okay, because it's going from 1/2 and it's automatically just changing to -4. So at this sharp turn, there's no tangent line, right? It could be, you could have a whole bunch of lines here that go through that point, okay, that are kind of tangent but not really tangent because there's no tangent line. It just automatically changes to -4. So at here, then, there's an open circle at -4, and it goes all the way to 1, and then it's an open circle again, okay? And then from here to here, the derivative is 0, right? So there's going to be a hole here at 1, and then it's going to go all the way to 4, and then there will be another open hole. So it would look like that. And then from 4 to 6, we have a derivative of 2. So up here, you would have an open hole, and then it would go all the way to here. And then if I defined this as a one-sided derivative at that end point, then I could do a closed circle. So at each of these points where it takes a sharp turn, the derivative is undefined, and in fact you can see that it's not continuous there because the slope is immediately changing and jumping to another value. Okay, so this is what the graph of this derivative would look like. And so that's a fairly simple example. So now let's try it with a regular function. So here, this is a nice smooth curve, and you know, at every point along this line, you know, you're going to have a tangent line. Right there it would be 0, right? And then as you go down, this would be negative, right? Then it would be 0, and then it would be positive. Okay? And so the derivative of the function here, and we're not going to be exact. Like this, I was able to calculate it exactly. Here, I don't even have a scale here. So I'm gonna just kind of approximate what this derivative is going to look like. Okay? So some important places, though, to make sure we identify on our graph of the derivative is right here where the derivative is equal to 0, and I'm going to come down and call this point C1. Okay, so there's like a C1 here, and at that point the derivative is 0. So whatever this derivative is doing, it's going to have to go through this axis. Okay. Now notice, before this point, the derivative is positive, right? It's really steep, and then it keeps going, and then it flattens out to 0. So it's going to be like positive coming down, okay? And then at this point, it's going to cross the axis. It's going to be 0, and then it's going to be negative, right? And then it's going to be the negative here. It's going to keep getting steeper and steeper. But notice that there's some point here and here. So this is another 0. Let's mark this on here first. This is another place. So it's going to get steeper and steeper and then level out again. And then this is another point where the graph is going to have a derivative of 0. And we'll call that like C2, right? Okay. So it'll be 0 here. So notice between here and here, it's negative the whole time. So it's going to be down here, and it's getting more negative, more and more negative, but there's going to be some point where this graph changes from being concave down to being concave up. And this is a really important concept. That point is known as an inflection point, and it's going to be like the steepest slope on this graph where it actually changes its concavity. And it almost looks like it happens. This is kind of unfortunate. I wish this whole thing was moved up a little bit, because it almost looks like that concavity is changing at the where it crosses the axis. That's not necessarily the case. Okay, this is a quality of the graph where it has the steepest point, and we'll call that like an inflection point. And I'll call that point like I. That's an inflection point. And so here, I is like somewhere like right here. Okay? And so this thing is going to be positive, and it's going to go to 0. Then it's going to be negative, and it's going to reach some steepest negative value, right? And then it's going to kind of flatten out and go back to 0. So they'll still be negative, but it'll go back to 0 until you get here, and then it'll keep getting larger and larger positive values. So this thing actually looks like this. And this is like the steepest point. And then it comes back up to C2. And then it goes back up. In fact, this thing looks a lot like a parabola, doesn't it? And in fact, this looks like a cubic function, doesn't it? And what we're going to learn when we do the shortcut rules is the derivative of a cubic is a quadratic. Okay? And so this actually shouldn't surprise us here that this ends up being the case. But notice this graph and this graph, very different, and it's just, there's a lot going on here, right? So the things to keep in mind are whenever this graph is positive, whenever the slopes are going up, you're going to be above the axis. Whenever these slopes are going down, you're going to be below the axis, okay? Which is what you have here. Whenever you have the horizontal tangents, you're going to have, the derivative is going to go through the axis, okay? And so, another thing to keep in mind is if I did raise this up, or if I did lower it, that would not change this derivative at all. The slopes would be the same. So if everything were raised up 100, it would be the same graph, and the slopes on the graph would be the same. And so the derivative is the same whenever you have a function, okay, that has a constant added to it or subtracted from it. When you take the derivative, any of those will have the same derivative. Okay, the constant just goes away. We're going to see that when we do the shortcut rules as well. Okay, so now let's try another one. I got a couple more examples here. So this says let f of t here, so we got this function f of t, let it be the growth of a population. Oh, by the way, I wanted to label these before we get to that. So if this one is y equals f of x, this is y equals f prime of x, right? If this is y equals f of x, this is y equals f prime of x. Okay? And so this is giving me f of t, and it says it's the growth of a population over time. And this is actually a very common, this is a realistic curve here, a population growth curve. I think maybe sometimes it's called a logistic curve. This is the sort of thing that you might see with like the spread of the coronavirus as it increases, but then it's going to level out. So the idea here is at the beginning when there's only a couple, people in the population, or a couple animals, whatever it is, in the population, okay, it's going to grow very slowly, but as the number of animals increase for that particular population, then the rate at which it grows is going to increase faster and faster and faster. And in a sense, that's like an exponential curve. If I kept this going, it would look like an exponential curve. But the thing is, it's not going to just keep increasing forever because there's a limited number of resources in any environment. So it's going to reach a steepest point, and then after that point, then it'll keep increasing, but the rate at which it increases goes down, and then it's going to level out at a certain value, okay? And that's like the saturation level for the population. So this is a common situation here. Well, what we want to do is we want to draw the derivative for this. So let's see if we can do that. So this is t, this is going to be y. So if we look for any horizontal tangent lines, we're actually, we don't have any. There's no place where it reaches a maximum value and goes back down. Let me make that point here. I didn't emphasize this, but these horizontal tangent lines are important because that's where a curve turns around. And so you're going to get a local maximum or a local minimum when the derivative is 0. So one way you identify these is you find when the derivative is equal to 0, and then you can find where these local min and max can occur. We're going to be doing that in the next chapter here. But here there are no actual completely horizontal tangent line. Here near the beginning it's close to 0, but not necessarily exactly 0. And here at the end it's leveling out, but it's kind of approaching this point here is like this saturation point, and it's getting infinitely close to that, but it's never like touching it and going back down. So there's never a horizontal tangent line to this graph. So this graph is never going to cross this axis here. Okay? And in fact, the population is always increasing, right? These slopes are always positive slopes. Okay? So this graph is always above the axis. The graphs are always positive. And so it's going to be close to 0 at the beginning, not quite 0. And then it's going to get steeper and steeper and increase. And notice this is another one of those places where this graph is going from concave up to concave down, right? Where it's changing its concavity, and I don't know, maybe about there. And so this is the inflection point. I'll call it I for an inflection point. And so that point is going to be important, so I'll mark it on here. And that inflection point, that's like when the rate of change is the fastest, because the rate of change is increasing, and you get to that inflection point, and then the rate of change starts decreasing. Okay, but it doesn't mean that the population isn't getting larger. It's still getting larger, but the rate at which it gets larger is getting less. Okay, and then it levels out, right? So it looks like this thing is near 0, and then it starts increasing, right, until it gets to a maximum rate of change, and then it goes back down. Then the slopes, the rate of change gets less and less, and it levels out and goes to 0. So it looks kind of like this. It looks kind of like a normal curve. Okay, and I didn't probably do that. This probably is getting closer to 0 than this. So it starts out, it's going up, and then this is the inflection point when it reaches its maximum rate of change, and then it starts going back down again, and then it levels out at 0, so it gets infinitely close to 0 without quite touching it. So, but again, so this is y equals f prime of t, and the rate of change is always positive. This graph is always increasing, never decreasing, so the graph is never below the axis. Okay, and it reaches that maximum rate of change when the rate of change starts decreasing, even though it's still positive. Okay, so this would be the derivative of that. So let's do one more example. This is similar to one that's in the homework. And so what we have here is kind of an application problem. And in this case, I'm told that the following graph gives the sales for the following years from like year 2000 to 2020. And so let's see here. So I want to answer the following question. So this is the amount of sales in millions. I don't know, let's say it's some business, right? And it looks like the sales took a real dip here from 2000 down to 2010, then it started increasing again. Okay, so first of all, it wants to know when did the sales increase and when did they decrease. Okay, so clearly they're decreasing here. So part A, I'm going to write the answers here. So they're decreasing here from like 2000 to about 2010, right? And then they're increasing from like 2010 to 2020. Okay, so they're decreasing the first half of the 20 years, increasing the second half of the 20 years. Okay, and then they want you to estimate the sales for each of these times. Okay, and maybe I'll just write it underneath each of those. So at 2000, I don't know, the sales is about 210. We'll say 210. At 2,500, at 2005, I don't know, about 100. At 2010, I don't know, about we'll say about 80 million, and then 2015 it's up here at about 150. Okay, so this is just getting the rate of this is just getting the value of the function at those different times. Now what it wants you to do is estimate the rate of change at those different times. So let's actually do that. Let's estimate the rate of change at each of those times. Okay, so at 2000, how are we going to do this? So here's 2000, and what I could do is I could do a tangent line, right? And then on this tangent line, so here at 2000, I said it was 210. So I'm going to just do like I'll do f prime of 2000, and then I'm going to do approximately. And so I'm going to do 210 for this y value, and then if I go up here at 2005, I don't know, that's like I'll say 1020, and then this is for 5 years, right? Or I could say 2000 minus, since this is my 2000 time, 2000 minus 2005. Okay, and so this is really like 100. This would be 100, or I'm sorry, 80, 90 divided by a negative 5 years. And so this would be negative, 5 goes into 90 18 times, so like negative 18. So this would be, the rate of change here would be a negative $18 million per year, right? So I could say dollars per year. And that would be like the rate of change, an estimate of the rate of change. So what I did is I used these 2 points on this tangent line. And this one was 2010 and this was 2000. Sorry, this was 2000 and then 210. This point was 2005 and 120. So I have these 2 points, and I found the slope of the line through those 2 points, and that line is approximately going to be equal to the slope of the tangent line. Okay, so it wants you to do this with 2000, 2005, 2010, 2015. Let me just say the 2010, that one's easy. It's going to be 0, right? F prime at 2010 is at least approximately 0, if not exactly. It's where it makes the turn, or close to there, right? And then you could find the slope here at this point if you wanted to. It's going to be a different tangent line. So let's actually do that. Let's do 2005. right? And I want f prime at 2005. Well, I know that this point here is 2005, 120. And then let me pick another point on here. So 2010, it's looks like it's 50. So this point here on the tangent line would be 2010 and 50. So using these two ordered pairs, I would get, I could do 120 minus 50, and then 2005 minus 2010. And so this would be 20 and another 50, so that'd be like negative, I'm sorry, no, that would be a positive 70 over a negative 5. And so this would be 70 would be like 14, so negative $14 million per year. So this would be negative 14. And then you could do it here for 2010, right? I'm sorry, we did 2010. So what did we say? 2015. So then there would be a tangent line right here. So let's go ahead and do what it asked us to do. Okay, well at 2015 then, f prime of 2015 is approximately. So at 2015, it looks like here. I'll write the ordered pairs down here. So it'd be like 2015, and at that it's like 110 maybe. And then if I pick another point on this tangent line here at 2020, it looks like I'm at 2,000 here. Or I'm at 200, right? So this would be like, I could do 200 minus 110 divided by 2020 minus 2015. And this would be equal to 90 minus 5, and that would be the 18, but now it's a positive $18 per year. So this tangent line is approximately equal to that tangent line, but in the positive direction. Okay. Okay, so what I'm doing is I'm estimating the rate of change by kind of drawing a tangent line and picking 2 points on the tangent line, one being the point on the graph, okay, and then another point on the tangent line, and then doing the difference quotient. And that gives me an approximate value of the tangent line. Well, now this asks me, when did the house prices drop the most rapidly, and when did they increase the most rapidly? So what this is actually asking for, okay, this graph is concave down and then it changes to concave up. And so this is when it asks did it drop the most rapidly, when is this line the most steepest before it starts becoming less steep. So that's the inflection point. So there's some point here where it's the steepest, and it's like somewhere between 2000 2005, I think. That is an inflection point here for when did it drop the most rapidly. And it's where the graph changes from concave down to concave up. Well, at some point it's going from concave up to concave down here. Okay, so there's some point when it increases the most rapidly, then it starts leveling out again. So there is another inflection point wherever it is, and this would be another somewhere between 2015 2020. That would be another inflection point when it goes, you know, where it's increasing the most rapidly before it starts before the rate of change, not the graph, not the sales. The sales is still increasing, but the rate at which it's increasing is decreasing. Okay, like I said, these take a lot of thought, a lot of thinking, okay, a lot of concentration here. So let's see. Finally, it wants us to graph the derivative of the sales. So this is y equals s of t. So it wants me to graph s prime of t. Okay, well notice it's both decreasing and increasing. So I only need a positive x or t axis. Okay, but I need it to be negative and positive here. Okay. And so let me do... So this would be 2000, 2005, 2010, 2015, and 2020. Okay, so at 2010, this is where your horizontal tangent line is, okay? So at this point, it's decreasing from the beginning, it's like decreasing the whole time. And then at this point, it changes to increasing. So on this half, you know, the graph is going to be underneath the axis. And then on this half, the graph is going to be above the x-axis, or the t-axis. So it'll be down here, over here, it'll be up here. Okay? Now, at the beginning, see, at the, like way here at the very beginning, it's almost like you got a horizontal tangent. Almost like if you went back, it maybe made another fluctuation. So you got something really close to 0 here to begin with, right? And then at 2000, it is, you know, it's getting more and more. But then when you reach this point here, this is like the first inflection point, I1, right? When you reach that point, that's when it gets to where it gets the steepest. That's where the sales is dropping the most rapidly. And then the rate of change at which it's dropping gets less and less until you hit 2010, right? And then it makes a turn, and then the derivative is positive. And then at this second inflection point, which looks like it's right about here, this is inflection point 2. Okay, it's a positive rate of change getting more and more, but then it hits this inflection point, and then the positive rate of change the positive rate of change starts decreasing. It's still positive, the sales is still increasing, okay, and it doesn't quite hit 0 at 2020, but it looks almost like if you kept going on, maybe it would be another fluctuation or something. Okay, so how are we going to do this then? Well, it starts really close to 0 here, and you come down to like this minimum negative rate of change. This is the maximum, the rate at which it's dropping the fastest, and then it comes up, and then it's going to pass through the axis here, and now it's a positive rate of change that's increasing, and then it's going to reach a maximum positive rate of change, and then it's going to go down, and then here at 2020 it's still positive, so it's not 0 yet, but if you kept going, it probably is going to make a turn, you know, and it might be 0. We just don't know what's going to happen after this mark. So the derivative for this would look like that. Okay? Now these are not the easiest questions, so you really got to think about them. And but it does draw together a lot of concepts. It helps you understand the idea of the derivative and how it's related to the function. Also, once again, if these sales went up or down by a constant, if the whole thing moved up, this graph would not change, right? You would still get the same rate of changes at each of those places. Oh, and you know, one thing I didn't do is, for example, at 2010 or at 2000, the rate of this should have been like a -18, right? I was going to do that because we actually calculated the rate of change at each of these places, right? At 2005, it was, this should be like a -14. So this thing probably should have made its turn and kind of gone up more a little bit. So I didn't do terribly good there, but that's okay. And then up here at 2015, it's 0. At 2015, this should be like +18. Okay, But oftentimes we're not paying as much attention to there. We're just wanting to see the behavior of the rate of change. So this here is y equals s prime of t. Okay, sales with respect to time. So there you go. That's the graph of the derivative and some of the problems that you could do.